Our goal tonight is to give communities and municipal leaders the information they need to make good decisions regarding these projects. Key topics to be addressed tonight are the drivers behind the increasing number of energy storage projects in New York, including information about state energy markets, policies, and programs, introductions to relevant energy storage technologies, overview of critical planning and zoning considerations, and fire safety and incident management. For this webinar, participants are muted and video is turned off to conserve bandwidth. Please enter your questions in the Q&A box at the bottom of your screen, and we will work through them at the end of the webinar. That will be facilitated by Tug Hill Commission staff. As you can see, we are recording this webinar, and it will be available on the Commission's YouTube channel later this week. So I will now introduce each of the speakers with a short bio, and then we'll go right into the presentations, and I won't have to interrupt again with introductions. So first, we have Ian Latimer, a program manager with NYSERDA's Clean Energy Siting Team, where he works directly with local governments, local and regional planners, and other stakeholders to pursue responsible clean energy deployment. His work addresses interdisciplinary challenges around local and state policymaking, land use planning and zoning, community engagement, environmental and social impact, and other related topics. Next, we have Dr. Ramesh Koripella, a principal member of technical staff at the Sandia National Laboratories since 2011. He is a materials scientist and engineer with more than 30 years of research and development experience in electronic components and power sources development. In the Energy Storage Systems Group, he performs technical analysis of different battery technologies and hydrogen storage technologies for grid storage applications. And lastly, we have Erin Minear, a program manager for the Energy Storage and Distributed Generation Program at EPRI. This research program aims to advance the responsible deployment of energy storage and other technologies with a key focus on safety, reliability, affordability, and environmental impacts. A registered professional engineer, Erin has over a decade of experience working on energy storage technologies. So with that, I will turn it over to Ian.
Thanks so much, Katie. And a sincere thank you to the Tug Hill Commission for the role that you guys play and the leadership you provide to your constituents and your communities. You do a wonderful job of getting, fact-based information out there to promote pragmatic and balanced approaches to, development of all kinds in your area. I just want to say again, we appreciate the opportunity here, and thank you so much for, creating space for us to have this conversation tonight. I will go ahead and share my screen, and you can just confirm for me that we are seeing what we should be seeing here.
Looks good.
Everything look okay? Perfect. And I'll say again, before we get into it, another thanks to Ramesh and Erin from Sandia and from EPRI, the Electric Power Research Institute, for both of you for being here today. Obviously, NYSERDA, we get a lot of opportunities to speak to our colleagues and, community members across the state of New York about technologies like energy storage and others. But we really appreciate the ability to bring in technical experts who are, doing nation-leading work across the country on these technologies. And so thank you guys for taking time out of your days to be here with us. I'll say a couple, quick ground rules, or it's not ground rules, but just things to keep in mind throughout the presentation. I always do my best to not give you stock images where I can avoid doing so. And to that point, just about every photo that's included in my slide deck is going to be a photo of an operating energy storage system that is actively providing a role or providing benefits and playing a role in the electric grid in New York to date. Wherever applicable, there's a little, box down here in the corner. I don't know if you can see my cursor, but a little box down here indicating where in the state the project is located. And I think that there's some things that you can keep in mind as you see imagery throughout the presentation today. So things like proximity to electric grid infrastructure, or proximal land uses, types of areas where we're seeing projects developed. Those are things to keep in mind as we see some photos and visual representations throughout the presentation today, just to sort of ground the fact that we're not talking about a hypothetical technology, right? We're not talking about a hypothetical piece of electrical infrastructure. This is real, and these are systems that are actively playing a role in the functioning of your electric grid today. The photo pictured here is a 20 megawatt standalone battery storage project, meaning standalone as in it's not directly connected to a generation source like solar or wind or a gas plant. Rather, it is plugged into the grid as an independent piece of equipment. And we'll talk more about that in just a minute. Um, a few different sections of the agenda tonight. We'll start off with some context. That'll be me, sort of speaking a bit about, again, the electric grid, markets, policies, and programs regarding energy storage in New York. Um, Ramesh and I will give you an introduction to energy storage technologies, including some non-lithium ion chemistries and technologies that are relevant in the energy storage market, and we'll see why that's relevant for the Tug Hill region in just a minute. We'll turn back to NYSERDA to talk about planning and zoning considerations, and then EPRI and NYSERDA will round us out with energy storage and fire safety. And then I'll plug some available resources for local governments, and we'll make sure that we try and leave as much time as possible for Q&A at the end. So we'll start big, start with the sort of high level, sort of thematic things to hit as part of this conversation. Another photo here of a 20 megawatt operating battery storage facility, this one up in the North Country in Chattagay. This is a NYPA owned facility. Why are we talking about energy storage? Honestly, you could strike the word storage from this slide and it would be just as relevant. Why are we talking so much about energy? Why are we having so many conversations? Why, if you're anything like me, when you open your Facebook feed, all you see is conversations about energy and utility bills. There's a lot happening in the energy space. Even before we started talking about international conflicts affecting commodity prices in the last few weeks, there were a lot of critical questions that were driving conversations about grid infrastructure planning and deployment. I'm going to sort of whittle them down to three major questions and terms that you can remember throughout the presentation. The first question is, do we have enough? And really specifically, do we have enough when we need it? And those are conversations and questions that fall into the bucket of resource adequacy, right? Do we have an adequate amount of resources to meet our needs from the electric grid? Can the grid withstand the strains and challenges that comes with things like seasonality and, extreme weather? Those are conversations that fall into the reliability or resilience bucket. And then finally, probably the one that is, most front of mind for people throughout the budget process in New York, certainly, but the higher level throughout, inflation and supply chain costs in the last few years. Questions about how do you make things more affordable, right? How do you avoid and minimize and manage, where not avoidable, the costs of investing and operating and maintaining a functional electric grid? That's the affordability conversation, right? So resource adequacy, reliability, affordability. Those are some of the key questions that anyone involved in running or maintaining the electric grid are asking themselves when it comes time to planning. The reason we're talking about energy storage in the context of those questions is that it has a key role to play for all three of those questions, regardless of what sort of level you're looking at it, right? If you're looking at, energy questions and concerns from a residential perspective, all the way up to the New York Independent Systems Operator, which runs New York's high voltage transmission grid and gets power from here to there to here, everyone sees the ability for energy storage to play a key role in answering those questions. We don't have the time to read everything on the screen, but you can sort of see with the icons across all these buckets, whether it's residential customers, commercial customers, utilities, the grid operator, there's a financial aspect to the value of deploying energy storage, right? The ability to reduce investments in more poles and wires, for example, or the ability to reduce the amount of electricity you're buying from the utility by installing a battery at your house. Across all of these different buckets, there's a real meaningful opportunity for energy storage, and that's a big part of why you're seeing that conversation. It's not the only one, although I'll say quickly, just sort of an example of how energy storage is not monolithic, right? It doesn't look one way, it doesn't act one way. You can have a battery that's installed in conjunction with a generation source like a wind plant. We call that co-located or paired energy storage. You can have a energy storage installation that's associated with load or a utility electric customer, right? So maybe a factory or a business wants to install a battery behind the meter to reduce their time of use billing and therefore spend less on their electric bills every month. You can have battery storage that's paired with a community solar project, which is directly giving a financial benefit to subscribers, whether it's residential or commercial subscribers in a community. You can automatically guarantee a 10 or 15% discount on your electric bill. Storage has a valuable role to play there in improving the economics of a community solar project. Again, similarly, you can have a battery that's paired with a small business to avoid, again, expensive utility costs. Um, there's all sorts of places that you can plug energy storage in and it can make sense, right? It really depends on the use case, it depends on the user, it depends on the technology that they're working with. For the most part here, we're talking about these larger batteries. I think a lot of people tend to not be so concerned about residential installations, although, as we'll talk about in the land use and planning part of the conversation, consideration for local regulations or where you want to make these things allowable can have serious implications for the ability of residents and businesses in your communities to be able to install battery storage. So it's worth having a critical understanding of how these are not one thing. They can look one way, they can act one way. It really depends on the user and the use case. Why else are we talking about energy storage? A couple other reasons. The first one would be that they are a critical contributor to grid operations and wholesale markets in the state of New York. So, the independent systems operator, the NYSO, and I apologize, it wouldn't be a state agency presentation without some acronyms that no one will understand or remember. So, my apologies from NYSERDA to the NYSO. Um, the NYSO they have two main functions. The first one is that they keep the grid running, right? They are the ones who are ensuring that we have the power and the infrastructure that we need to ensure that there is electricity on demand for New Yorkers. The second thing that they do is they administer the competitive markets by which we ensure that we're getting as good a deal as possible for our electricity. And there's a few different markets that they administer. The first one are the energy markets, which is where power plants or producers or generators, that is where they are committing their ability to deliver you a certain amount of electrons at a certain price. And that price of predictability is what allows utilities and other electric purchasers or electric, you may hear them referred to as ESCOs, other, people who are buying electricity on the markets for delivery or benefits to, individual utility customers. They are buying their energy markets through an auction that is administered by the NYSO. Battery storage projects have the ability to play a role in that in those wholesale energy markets, by which they're able to compete with other generating facilities like a renewable generator or a gas plant or a nuclear plant. They are able to say, we are capable of giving you, X megawatt hours of electricity tomorrow at this cost. And it is a competitive bidding process from there. And it tends to be a cheaper cost compared to some of the other sources of electricity. There are also other markets, however, that some of those other plants are not able to fill a role in, right? Not every nuclear plant or gas plant is able to compete in these other markets, which provide better services to the grid, such as the ancillary services market, which includes things like voltage support, frequency control, operating reserves. I recognize that those are things that don't mean a lot, so I'll try and very quickly explain what they mean. Basically, at any given time, the electric grid is, man's greatest invention, and supply and demand have to be exactly the same. Otherwise, you risk tripping a fault that could trigger the whole grid to go offline. Battery storage, in particular, because it is able to respond to charging and discharging signals as quickly as it can, is able to play role in this ancillary services market that other traditional energy generation sources cannot always play. And then finally, they operate a capacity market. And the capacity market is a longer term planning tool by which the NYSO is trying to make sure that on the whole, throughout the year at any given time, we have enough operating power plants and energy storage infrastructure to meet our peak demand, right? So winter peaks and summer peaks, when we are using the most electricity, when it's the coldest and everybody is using electric heaters, or when it's the hottest and we're using our air conditioners, year round, we need to make sure that we are supporting enough assets to be online so that when we need them, they are there. And that's something that we do through administering a capacity market. Now, it's important to mention because, again, energy storage is able to play a role in a capacity market that not all generation sources can play. Wind and solar as intermittent resources, they are not always able to provide the same value in a capacity market because they are, again, intermittent. They are variable in terms of their production. So energy storage has a really key role to play in these various markets in a way that is different from some other technologies. And then finally, with regard to operations of the grid, I'll just quickly mention the electric utilities also run procurements whereby they also build battery storage projects as a way of spending less money on building new poles and wires. They typically call those non-wires alternative projects. And so I mention all of that because there's a lot of interest in these technologies from different people at different levels of keeping a functioning electric grid, and that includes utilities and the NYSO at the top. Finally, why are we talking about energy storage? Load growth. For the first time in decades, the state of New York and across the country, really, we are seeing a demand for electricity that is unlike anything that we've seen in a long time, certainly in my lifetime. And that's driven by a few things. It's driven by investments in advanced manufacturing and other economic development projects, things that regions of the state and regions of the country really want in order to get those job creators, in order to get advanced manufacturing opportunities, you need a lot of power and you need it reliably. Energy storage can play a critical role in that. Um, Construction of data centers, which is a really controversial topic. The reality is that some of those data centers, they are applying for interconnection through the NYSO as a large load or a large customer. And as such, the NYSO, the people responsible for running the grid, it is their job to make sure that we have adequate resources to respond to them. And so there's that. There's consumer and transportation electrification, right? So people using heat pumps, people using electric vehicles, all of those things are contributing to requiring more electricity than we have been used to. Load growth has been pretty stagnant for decades and is now, rapidly increasing all around the country. Very quickly, we'll just say that you'll hear throughout the presentation, people refer to capacity, both in terms of watts or in terms of watt hours. And so I'll just very quickly say watts are a measurement of power, i.e. the rate at which something can generate electricity, right? So like a power plant will typically say it's, a 20 megawatt plant, which means it's capable at its maximum of generating 20 megawatts worth of power. Energy storage capacity is typically included with a time duration element, which is watt hours. So it's a measurement of energy, i.e., how much power can be discharged or taken on over the course of time. And so you'll hear kilowatt hours, megawatt hours, gigawatt hours, things like that. That's what that's referring to as really storage capacity, which is different than like the generating nameplate capacity of a solar or wind project. I know everyone's curious about my very bad, clunky analogy considering the container. All of it is to say that let's say you have three tubs that are identical in height, but not in width and storage capacity. If they have the same size hole coming out, or like a same size hole at the bottom, if you took a snapshot, all three of them would be discharging the same amount of water at any given moment. But the storage capacity can be so different, right? So sometimes the watt or the power rating can be similar for different assets, but the storage capacity can be very different. Clunky analogy, you'll have to forgive me. Um, NYSERDA has programs that are supporting everything from residential to bulk or large scale storage. I'm going to quickly go through them because we've got other expert presenters we want to get to. We'll just say that, again, NYSERDA programs exist to support residential storage, retail storage, which we would consider, commercial installation, or even up to like a community solar size project. And then there's the large scale bulk projects. These installations, with the exception of the residential one, because I'm not allowed to post photos of New Yorkers' garages, the other three photos are projects in New York, one in Westchester County, one in the Bronx, and then the other one is actually a photo we saw earlier of the project in Stillwater. Um, Why are we having this conversation specifically with our friends at the Tug Hill Commission? NYSERDA is currently running a bulk procurement for large-scale storage projects, which is the function of years of state policy making and discussions with the Public Service Commission about how best to do a competitive procurement for these large-scale storage projects. The reason we're having this conversation is that there are a handful of projects participating in the procurement, located throughout the Tug Hill region, and uniquely, those projects that are proposed are non-lithium ion battery chemistries. But the reason I wanted to show this graphic is to show you that lithium ion batteries are by far the most, or the vast majority of the projects participating in the active procurement. So we're going to talk about lithium ion, even though for the sake of this procurement, the projects proposed are non-lithium ion batteries. We will also talk about those technologies, and that's why our friends from Sandia National Labs and EPRI are here to talk to us today. With that in mind, I'm going to quickly keep us moving to talk about introduction to energy storage technologies. I will quickly start by introducing, some of the context in New York and lithium-ion batteries in particular, and then I'll turn to Ramesh to take me to school, along with the rest of us, about some of the other chemistries that we're talking about in the world of energy storage. Real quick, this is a photo again of a 20 megawatt battery storage facility out in Western New York in the town of Orangeville. It's paired with a wind farm you can see in the background. It's the Orangeville Wind and Storage Facility. And again, when you look at this, what are we thinking about? We're thinking about proximity to grid infrastructure, right? There's a substation that's located just across the road. We're in likely a rural residential district, proximal land uses, you're not seeing a ton of development in the immediate area, things like that. Um, I'll skip this. Energy storage can look a number of different ways, but I'll just quickly say, can be chemical energy storage, can be mechanical, can be thermal. Ramesh will, talk us through some of those options and what they mean in greater detail. But I'll say, with a couple of examples, that these again are not hypothetical technologies, right? So energy storage as a concept is actively at work and exists today. We've got gravitational potential energy storage with pumped hydro, both at the Blenheim Gilboa, but also out in Niagara Falls. You've got mechanical energy storage. There's a 20 megawatt flywheel project that was developed 15 years ago in the capital region. You've got another photo of that project in Stillwater, the lithium ion battery project there. There's currently almost 530 megawatts of deployed battery energy storage capacity specifically. So that's not including, energy storage, not including the pumped hydro facilities in New York. And I'll also just say, sometimes we get questions about the scale and, why we need big batteries and small batteries and all of that. And I would just say, um, another example of energy storage that I think gets lost in the conversation is when we think about fuel, right? Fuel is also a form of energy storage. We are storing, energy. It's the chemical potential energy of gasoline and diesel and other fuels. And when you think about the infrastructure needed to make sure that we have the fuel that we need at all of these various endpoints, suddenly you need infrastructure to support that, right? So whether it's large, bunker, fuel tanks, or whether it's distribution facilities, or the bottom left photo is an example of gas station tanks, or the gas tank in your car, or the fuel can in your garage. There are all of these scales at which energy storage for, gasoline is critical, right? And you would never say, well, if we all just had gas tanks in our cars, then we'd be good, right? Because that's not really how it works, right? You need the necessary infrastructure and distribution systems and supply chains set up to ensure that when you need it, your car has gasoline in it. And it's the same thing with electricity, right? We're talking about infrastructure on a massive scale, everything from, residential and commercial businesses all the way up to large scale grid serving installations.
Ian, can I
Um,
interrupt you for 1 second?
yeah,
We had a
please.
question, the slide with the map with showing where the energy storage bulk, yeah, right there.
Yeah.
Can you just explain the colors and what they mean, please?
Yeah,
The green, the
sure.
purple, the orange?
Yeah, so it's just icons that are referring to the technology of the installation proposed. So the green ones are lithium ion batteries. The orange ones, I'm trying to look at the iconography here, and I can confirm in the chat once I'm not presenting, because unfortunately when I'm screen sharing, I really can only see that. Two of the projects are zinc halide batteries, which is also a battery energy storage technology, but with a different chemistry. Two of them are compressed CO2 projects, which is using the compression of a gas to store energy for dispatch at a later time. And then the third one is a advanced compressed air energy storage project, which is similar in terms of the mechanics compared to the CO2 projects, but using a different type of gas as the storage mechanism. And we will include a link. I included a link here, but I can confirm and reiterate the color scheme in the comments once I'm not presenting.
Okay, thank you. And then one other question we have is, will participants be able to get the PDF of this presentation after
Yeah.
the present? Okay, perfect. Thank you.
Yeah, absolutely. Yeah, we'll make sure the slides are shareable, any links as well as contact information for the team at NYSERDA
Thank you.
available. Yeah, no problem. Just keep us moving to make sure we get to Ramesh. So just quickly, we'll just say a couple more things before we turn it to Ramesh. Majority of energy storage being deployed today is battery energy storage, and that's for a few reasons. Technology maturity, falling costs, the siting considerations, because these are often smaller and modular systems that don't require as big of a footprint. Efficiency, energy density, the scalability of these modular systems, things like that. And capacity has really increased, year over year across the country, even in places you wouldn't expect it. I believe, and maybe my friends from EPRI can confirm once they're speaking later, I believe that the state that installed the most battery storage last year was Texas, a state that does not have clean energy mandates, a state that does not have incentives available to support those technologies, and yet leads the country in terms of the deployment of battery storage. And it's because it makes economical sense and it makes technological sense to keep a mature grid operating. Um, Within the battery storage world, when we talk about battery energy storage systems, we're talking about, again, very modular and scalable building blocks. So cells that are wired to become modules, which are wired to become racks. And then you add in some other equipment, including a battery management system to act as the sort of eyes, ears, and brains of your installation, as well as balance of system equipment, which will depend on the technology, right? So, for example, with a lithium ion battery, in accordance with the fire code that we'll be talking about later, we know that we need off-gas detection and fire suppression and ventilation systems built into the equipment. Those are all things that are all coming together to make up what we would consider a battery energy storage system. Mentioned the battery management system, and I can talk about that a little bit more later, but want to make sure that we've got time for Ramesh. Battery chemistries are constantly evolving. The safety, cost, energy density, physical footprint, the efficiency in charging and discharging, those are all factors that are constantly leading to, improvement in the type of batteries that are being deployed. And as a result of that, there's different chemistries that are available for different purposes, right? Not every car battery is a lithium ion battery, right? You've got lead acid batteries, you've got alkaline batteries for commercial uses, you've got nickel-based batteries. There's all sorts of chemistries that are usable for different things. Lithium ion has become the prevailing chemistry specifically for shorter duration battery storage projects, like 4 hour duration, for example, where it's capable of discharging its capacity over the course of 4 hours. Um, Lithium ion has become a prevailing chemistry for a few reasons. Number one, it's really efficient. Um, it does not take long to build and source relative to other chemistries because it's a very robust supply chain. It's a very, common consumer good. Typically, once operating, the costs of operations are low. They do not require a lot of space relative to other technologies, and they're able to last for a long time. You can do a lot of charging and discharging cycles before, you need to think about replacing or retrofitting your installation. And batteries will continue to evolve. The primary thing I would say that's being considered in the evolution of battery chemistries is safety, right? Reducing the risk of fires and explosions and other safety concerns associated with these technologies, which we'll be talking about later in the presentation. Falling costs, increased energy density, things like that. Final quick shout out before I turn it over to Ramesh would be. That within the state of New York, we're really fortunate to have a good friend here, Dr. Stan Whittingham, who is a Nobel laureate for his role in helping invent the lithium ion battery. So I'll just say that in addition to this not being a hypothetical technology in terms of it playing a role in the grid today, it's also not a hypothetical in terms of what it means for New York, right? You've got the New Energy New York Coalition led by Dr. Whittingham and others out of Binghamton, which is helping New York be at the forefront of an industry, much like we've been with GE and other, technological leaders for, century. And so, yeah, I'll pause there. I'll welcome Dr. Ramesh Koripella to take over, and I will stop sharing my screen so that you can go ahead and do that, Ramesh.
Already. Thank you, Ian. Can you see my slides?
I cannot see your slides yet, but I do hear you just fine.
Okay, hold on 1 minute. Probably it didn't come through sharing.
Now we are seeing it. You might want to go to presenter mode if that will allow you
Okay.
to, but we do see your screen.
Okay. Thank you. Hi. Good evening, everyone. My name is Ramesh Koripella. I work in Sandia National Labs in the energy storage area. I'm located in Albuquerque, New Mexico. In this talk, we'll cover different energy storage technologies briefly. Um, you can broadly divide the energy storage technologies into these four broad categories. Electrochemical storage, that includes all types of batteries: lithium-ion battery, sodium-ion battery, lead-acid battery, zinc batteries, metal air batteries, flow batteries, including supercapacitors. These are all electrochemical type. And then you have another category called mechanical storage. These are pumped hydro storage, variations of pumped hydro storage. Pumped hydro storage is, as Ian mentioned, you basically um, pump water between one reservoir to another reservoir. A couple of slides on that I'll show. And then gravity storage, compressed air, flywheels, these are all mechanical related. And then the other two categories, I'll just mention it here, but I don't have any slides on them. Thermal storage and chemical storage. Thermal storage is you convert the electrical energy into heat and then store the heat into either molten salt or in a sand or in a some kind of porous rock or a insulated brick. Somehow store it, and then when you want to generate power, you use a working fluid like air or some other gas, inert gas, and bring the heat and run your gas turbine. There are a few companies working in that area. The reason I didn't show is these are still a lot of them are in the early stage development, and also they are efficiency wise, they are more efficient if you put them close to a facility that can also use the heat. Then it makes more sense, but rather than just putting on its own. And then chemical storage is convert the electricity into hydrogen gas or convert the hydrogen gas into like hydrocarbon gas like methane or into ammonia. This is good for like seasonal storage for very long duration. In fact, really, we don't have any other way of storing for very, very long time unless it's some kind of chemical form. So that's where it comes in handy. But right now, the way we do it with electrolysis, generating hydrogen, combusting hydrogen into a gas turbine or converting into electricity with a fuel cell, these whole process is kind of low efficiency. The whole thing is maybe about 39% efficient. So it's not really a good way to store your electricity unless you really need it. So those are the four different categories in broadly. What are some of the desired characteristics of an energy storage system? You want to respond quickly for load demand. Like if the technology requires some startup time, for example, then it cannot meet some applications like frequency response, which requires very quick response for a battery or any energy storage system. Some can do it, some cannot do it. So that's why you need to understand it may not meet the frequency response type application, but they may be good for long duration energy storage. So it's depending on the application. You need the right energy storage technology. You want to have a high round trip efficiency. That means how much energy you can take it out versus how much energy you are putting in. You want to have a very high efficiency and low self discharge. You can think of it as like a leakage, right? You don't want to leakage too much, so you want to have a low self discharge and high energy density. That means how much space it occupies. High energy density occupies less space. It is not a very big concern for stationary storage, but if you are In automotive applications, energy density is important because you want your car to go long distance. You want it to be cost competitive, environmentally friendly with less toxic substances, and good supply chain, and you want it to be safe. Like lithium batteries, which is currently the most dominant technology, it's good in a lot of these respects, except last two. Most of the batteries are made in China right now, so we import a lot of these lithium-ion battery cells. They're trying to start up some manufacturing in the United States, but still all the raw materials are made in China. And then safety, we had, as you all know, there are some notable safety incidents with lithium-ion batteries. So there's still some concerns. They're getting better, but still there are some safety issues with that. Of all these technologies I talked about, the most used, deployed right now are the pumped hydro storage. It's been there for a long time. And then the lithium-ion batteries is picking up more. The others are just either they are in the early stages of deployment or the people are still talking about it. As a brief, what is an electrochemical cell or a battery? It is two electrodes in an electrolyte separated with a ion conducting separator. That's basically what a battery is, right? Any battery is like that. So every battery has a negative terminal and a positive terminal. Electrochemists call them anode and cathode. In lithium-ion battery, my anode is a graphite layered structure, and cathode is a layered lithium oxide or lithium phosphate type material. So during discharge, the lithium ions, these are both layered structures. Lithium ions basically literally move from anode to the cathode side. It intercalates in between those two, and the process reverses during charging. So how they make this battery is you have this separator. These are like a plastic film. Polyethylene is a polypropylene, and then they print this anode and cathode on both sides, and then put the current collector. One side is aluminum foil, other side is a copper foil on the anode side. Then you jelly roll them, and then put it in a can, then fill that with electrolyte and seal it. That's how the battery is. Why you can't use aluminum on both sides is because aluminum reacts with the lithium on the anode side. So it need to have two different copper and aluminum for lithium battery. What are some of the electrolyte is a lithium fluorophosphate type electrolyte. It's dissolved in some organic solvent, ethylene glycol, methylene dimethylene glycol type collectors. So what are some of the important characteristics of any battery? Voltage, right? You're talking about single cell voltage. That depends upon the electrode you're using and the electrolyte. So if you want higher, like when you buy a battery, like a 12 volt battery, they're not really, single cell is not producing 12 volts, but they put together several cells to make 12 volts. Similar thing, 9 volt battery. So each cell voltage is small. Lithium battery is one of the batteries has higher voltage, like 3 point something, 3.2 or something. Most of the other batteries are 1.5 or 1.2 volts, single cell voltage. Current is how much current can you draw from the battery. It depends upon the area of how much area you have in the battery. Also reaction rate, how many coulombs you can draw from it. And the power is voltage times current. And the capacity is typically expressed as amp hours or watt hours. It's an important measure. Like when you say I have a 1 amp hour battery, what does it mean? That means if I draw 1 amps from the battery, it will last for 1 hour. That is, they call it C rate. So if I discharge it, for example, at half the C rate, that means that only I'm drawing half an amp, then it will last for 2 hours. If I discharge very fast, like 2 C rate, then it will last only less time, half an hour. If you draw less current, it draws 2 hours. 2 hours, right? It will last 2 hours. So that C rate is important because depending upon the application, most batteries, lithium batteries operate at 0.5 to 1 C rate. But in some applications like frequency response or quick response applications, you may be asked to draw at a higher C rate like 2C or 4C. And you want to have a high round trip efficiency, and talked about self-discharge. You want to have low self-discharge, and degradation is most cycle life. How many cycles you can operate this battery and how long it lasts, calendar life. Typical lithium-ion battery is good for about 3,000 cycles. Some technologies, they last very long cycles, but some not as good. Calendar life, lithium-ion batteries, typically 10 to 15 years lifetime. This is any battery. You see, when you try to draw current from the battery, you see this kind of behavior. When battery is not connected to any load, it has certain voltage, right? That's called open circuit voltage. As soon as you try to draw current, you see this kind of behavior. You see large region of flat region. That is where you want to operate your battery mostly, and don't want to go to very high extremes, this or that one. In this region, your battery management system controls it to try to operate within the safe limits. If you go very high, then you could run into bad condition, because when you're trying to draw current from the battery, you also generate heat. The heat comes from the inefficiency of the battery. How much energy you are discharging or how much energy you need to put it in. You want to have very high efficiency. Lithium batteries operate at 85% to 90% efficiency, but that means still 10% inefficiency that is converted into heat. If you're drawing too much power, that it could generate a lot of heat that could go into unsafe conditions. So you want to avoid that one. So there are different types of lithium-ion batteries. It is most dominant technology for 4-hour duration right now. But as the battery costs are going down, they are becoming competitive for 8 to 10 hours also. They support wide range of duty cycles with good round trip efficiency. Still, safety and cost are major concern for very long duration energy storage. As I said, there are different flavors called LFP, NMC. What these are differences are, anode is still graphite, but cathodes are the different cathodes. So each cathode gives different voltage and different how much power capacity you can store. High capacity batteries are cobalt based thing, but they're also a little bit unsafe. For cars in the early stage, they're all used very high energy density because you want to push the car, far, right? But for energy storage, industry is moving towards LFP. It's slightly lower energy density, but it's much safer compared to the other lithium battery technologies, less prone for thermal runaway. They can operate theoretically over a wide range, but preferably in this range. If you go to very low temperature, efficiency is not as good. High temperature also not as good because it's already at high temperature and you need to dissipate some heat from the storage that you need to put it in, otherwise it gets too hot. So you need to put them in a air conditioning enclosure, or battery cooling system is needed to keep the battery in the safe operating zone. You might have heard solid state batteries, right? They're coming up, they're safe. These are still in the early commercialization stage. They use a solid electrolyte separator because you don't have the organic electrolyte and organic polymer separator. So they have less combustible materials. So they're slightly better safety and also higher energy density. But thermal runaway risk is not completely eliminated because your lithium and cathode, it is oxide material, right? You have oxygen in there already. So even if you don't have oxygen from outside, that one and your battery, that can ignite the battery. Once it ignites, it can go into thermal runaway. But because you don't have a lot of organic materials, so it's not as bad compared to the other ones. A little bit about sodium batteries. Sodium, there is a lot of excitement right now about sodium ion batteries for two reasons. One, they use earth abundant materials. They're lower in cost and they're safe. I put a question mark because they also can go into thermal runaway, um, but not as bad as sodium ion batteries. They're relatively much safer. They are not yet in high volume commercial manufacturing, not in the US, but they're in China. They're much more advanced than in the US. There are two types of sodium ion batteries. One is high temperature batteries, other one is low temperature. I quickly mentioned high temperature, but they're not being used right now very often. These molten sodium sulfur batteries, NGK and BASF, they both try to commercialize it and they both pulled out of market. And then there are metal halide batteries, nickel metal chloride batteries. General Electric, they were manufacturing these batteries in New York, Schenectady. They shut down their factory about 10 years ago. At that time, they're not really, the energy storage technology didn't pick up as much, but they're looking for them for also for transportation application for like locomotive and other things. But they use ceramic membranes and the breakage and safety issues. They ran into a lot of issues and then they finally shut down the whole operation. Now they're using technology developed low temperature sodium ion batteries. These are very analogous to lithium ion batteries. Basically, you have a polymer separator, anode and cathode. Anode is right now most of them use hard carbon, and cathode again there are different types of layered structures and other types are there. The most dominant companies are um, some of the companies actually I should mention because they went bankrupt or acquired. They're also going through a lot of changes. Faradian, it's a UK-based company. They one of the early company developed this technology. They've been acquired by Reliance, Indian company. Natron, this is a California-based company. They also developed a sodium ion battery. They're setting up a manufacturing plant in Kentucky, and they declared bankruptcy. These Haina, CATL, these are all Chinese companies. Northvolt, this is a Swiss company. They set up a manufacturing plant. They declared bankruptcy and their assets are acquired by Lighten. They're still making some high voltage sodium ion batteries, but small manufacturing. There are few US companies looking into this market are Peak Power, Unigrid, Alsem. There are a few other companies, but these are three a little bit dominant. Peak Power, they don't make their sodium cells, but they're sourcing from China, but they assemble the cells here. Their marketing strategies, they think they can be cost competitive with lithium ion batteries for long duration energy storage market in the grid scale because it doesn't need AC or cooling. They can use a simple air cooling and the chemistry is safer. So they think they can be cost competitive because of the OPEX is lower. So they're doing some major installation in Colorado and then they signed up for a few other contracts. We'll see once they put it in how they perform. Right now, we don't have too much data. This is Unigrid came out of UC San Diego. They're also developing a sodium ion battery. They're making good progress in commercializing it, but we haven't seen large installations yet to really gauge how they're performing in same thing here. So again, to conclude, sodium ion batteries, they offer better low temperature. They also work better at low temperature compared to lithium ion batteries. You can go to -20 without any problem. They work better. They can be charged and discharged faster than lithium ion batteries. Another advantage is you can store them with zero voltage. Like lithium ion batteries, you never wanna take down to zero voltage. They always leave at some certain voltage charge, and that's how they ship it. So because you can discharge it fully, these batteries, they're safe for transportation.
Hi,
And
Ramesh. I'm sorry to interrupt. I just want to make sure that we've got some time. Would you mind if we move to some of the compressed gas and zinc halide
yeah,
portions?
I will. Yeah. But as I said, the main challenges here are cycle life and increasing energy density and scaling up for high volume manufacturing. Good progress is being made, but they're still there. As Ian mentioned, Stanley Brigham University, Noble Heritage lithium-ion battery. If you ask his opinion, he doesn't share the same enthusiasm for sodium-ion batteries. He thinks lithium-ion batteries is the way to go because of higher energy density. Yeah. So anyway, so I he wanted me to go to other batteries. So let me quickly touch on the other batteries. Flow batteries. You might have heard of flow batteries, right? Flow batteries are slightly different from regular lithium-ion batteries and other things in the sense here the reactants are stored in these electrolyte tanks, large volume tanks. Um, so analogy would be like your car. Your car engine is your this battery stack, and the your fuel tank is these tanks. Because you're separating um, engine and the tank, so you can theoretically, um, if you want to make it for long duration, you just put a larger tank. So um, that is how they're selling this technology. Theoretically, yes, but on actual use, the energy density of these are slightly lower. That means you need to use a dilute solution. Because of that one, you need a bigger tank. That's one problem. And then you need to have the pumps, you need to have sensors, controls. So the auxiliaries, everything takes up some thing, and the energy density is lower, like 65 to 75% versus 85 to 95%. So there are a few companies you might have heard: redox flow battery, vanadium redox flow battery, Infinity, Canadian company; iron flow battery in ESS, that is there in Oregon; zinc bromine flow battery, red flow. This company went bankrupt. This is Australian company. But there is another zinc bromine hybrid battery, ES. These are in New Jersey. I have one slide on that one. CM Blue, a German company. So there are companies looking at it, but we don't know. And if you go to zinc batteries, zinc nickel, zinc manganese, zinc air, zinc halide, there are a lot of zinc batteries. In fact, zinc batteries are one of the first batteries that have been ever developed. Old people like me probably remembers zinc carbon battery, all everyday batteries. They're all zinc carbon batteries, right? They're very good for primary batteries, but it's very difficult to make rechargeable batteries. Finally, there are some rechargeable zinc batteries coming. Zinc nickel, this company Zinc 5 is in Oregon. They are making these batteries. They are very good for high power pulse power applications, good for like AI data centers. Zinc manganese, these are out of Urban Electric Power, startup out of City College of New York. These are early stages of commercialization. They tied up with the Indian company to commercialize it. Zinc Air, this is E-Zinc, it's in Toronto. They are also in the early stage of commercialization. Zinc halide, I talked about flow type, right? Red flow, but EOS is the company in New Jersey. Let me quickly go into that. This is how they're making the batteries, the ES company. They had a very innovative passive design battery. No active pumping, nothing. It's just like you see, it looked like a lead acid battery, right? So it's a 1 kilowatt battery. They're making several of these batteries and collect them in series or parallel to get to the stage you need. So this is their Gen 3 batteries. They're increasing the energy density. They're putting 40 cells versus 20 cells. This is 2 kilowatts and also higher energy density compared to the earlier one. They're using carbon here for the uh, anode and carbon composite for cathode for cost reduction. Here they're using titanium based materials, a little bit expensive for cathode. This is how they look like in a 20-foot container. Inside, if you look at, they stack batteries along the walls. The 6 rows, this is the old version, but new one may be different. So there are 12 batteries in series, and all the battery management is outside. They have a fan for circulating air to dissipate the heat. And
Ramesh,
pumped hydros.
can I
Yeah.
just interrupt real quick? We have just a couple questions.
Okay. Go ahead.
Are are sodium chemistries prone to challenges of expansion as they are charged?
Yes and no. Some of them are, yes, they do, but it's not as bad as the lithium oxides and lithium phosphate type batteries. Yes, they do. They
Okay.
do expand and contract.
And then the other question, which is probably going to be a follow-up after the webinar, we have an individual who would like to see some graphs that shows battery storage capacity variations over the course of a year. So, during cold weather, during warm weather, and how they discharge, that kind of thing. So maybe that can be a follow-up.
Yeah, I don't have a chart on that button, but that's a very good question because some batteries, as I said, sodium-ion batteries work good at low temperature operation. But lithium ion, you need heating to keep them warm. Otherwise, you drop capacity.
Right there.
Yeah, yeah.
Okay, thank you.
So
And then the next question is going to lead right into your mechanical storage. So I won't ask you that one yet. You'll probably answer it. Thanks.
okay, pump rate storage is basically you pumping the water between two tanks, um, one at a higher elevation, one at a lower elevation. It can be closed loop or a open loop. Open loop will be like put it close to a hydroelectric plant. So it's already have hydroelectric plant, put some storage in it. It's very mature technology. It's good for 4 to 24 hours. To do this, only thing you need to do is you need to have a reversible pump here, right? It's not only generation, it also can pump. But most of the old turbines they are fixed speed, so they cannot support variable generation. But some of the newer turbines, they can do that one also. So they can meet a lot of energy storage applications. So high capital investment, but storage cost is low. So the other one is there are some variation of the pumped hydro storage. Few people are looking at it. And then gravity based, you must have heard these concrete blocks and cranes moving up and down, or the concrete blocks on railroads moving on inclined railroads. These are all in the early stage of commercialization. They're not been shown commercial viability yet. And then compressed air storage, you take the electrical energy, compress the air, and store it in underground, or you can also store it above ground too. When you compress air, you generate heat, right? So if you capture the heat, it's called adiabatic compressed or advanced energy storage. If you don't capture the heat, then it's diabatic. It's a lower efficiency. It's a higher efficiency. And instead of air, you can also compress CO2. That's what CO2 dome company do. And of course, flywheels also come into this same category. They are commercial. They've been used in the energy storage for frequency response. I said they're good for short duration, but not very good for long duration because you have to put several of them and then it gets expensive. And also the safety issues also, if you put too many of them. So we talked about compressed air, adiabatic and diabatic. Let's go to the next slide, talk about a little bit about CO2 dome. So this is the dome inside it. This is outside is a rigid dome. Inside they have a bladder. That is where they keep the carbon dioxide. So when charging, you move the carbon dioxide through a compressor. You compress the carbon dioxide, make them into liquid. You capture the heat of compression in a heat exchanger, and then store the carbon dioxide in the tanks and outside in the big tanks, liquid carbon dioxide. When you want to generate power, you convert the liquid carbon dioxide again into carbon dioxide gas using some of the heat that you stored here, and then run a gas turbine, and then move the gas back into the dome, inflate it. So it's dome going up and down. That's how it works. So they did a proof of concept with the Italian company in Italy. They are putting several installations in the US. They haven't done complete installations yet, so we don't know how the performance what are the round trip efficiencies, operating costs, self-discharge losses, etc. Hydro storage also same. This is a Canadian company. They did a small demonstration project in, I believe, Ontario, um, but they haven't done any large-scale demonstrations yet. And QuidNet Energy, it's a small variation of this one. They want to pump this water into these underground rock caverns or split rock, store it under pressure, and then move it back. Let me show you in the next slide. Actually, it'll be better. This company called SAGE, they are doing this similar demonstration project. All these companies came out of oil and gas industry. If people remember the fracking, right? You put high pressure water in between the shale rocks and you separate the rocks and you get the oil out, right? Once you get the oil out, you can put water into that one and then you can flex these rocks up and down to charge and discharge. You don't want to charge completely, discharge, or completely charge it to create the rocks big or collapse the thing. But as long as you can flex it elastically, it's like breathing. So they did a demonstration project in Texas. So it's a promising technology, something to watch actually. And this company, RCAM or Spera, this is NYSERDA funded this work, some of this work, and they're still in the R&D stage. They want to build these big concrete cylinders. They want to put it underwater. They want to put it close to offshore power generation. Basically, water moving in and out for charging and discharging. So in summary, right, you have a lot of different types of energy storage technologies. We didn't talk about thermal and chemical, but for short duration, lithium-ion battery is still the dominant technology because it's readily available, it's cost competitive, and that in they are getting safer actually. Originally, they have some bad incidents, but they're moving towards LFP chemistry. And also the safety codes and regulations are in place right now for to ensure better quality and safety. And also most of the installations are moving from indoor to outdoor. In old installations, some of in California, they have some indoor installation that's where big fire and made a lot of problem. In outdoors, into modular containers, the idea being you can contain the fire to one module, doesn't spread to other modules. Like in the big fire in Australia, for example, um, um, Tesla battery, they were able to contain it because it's modular. It's one container. So sodium-ion batteries are emerging technology. They may be competitive lithium-ion battery in few years. Pumped hydro storage is currently the largest grid-scale energy storage technology. And for long duration energy storage, you have several different technologies. These are all in the early stages of commercialization. Thank you very much.
One
I'll
quick
get
question,
back.
Ramesh.
Yes.
If you had to compare the efficiency of hydro pumping storage versus compressed air, what's more efficient?
Pumped hydro, definitely.
Oh,
Pumped
thank you.
hydro, because you don't have any heat losses there. It's very high efficient versus compressed air. You have you generate heat, right? You have to take the heat. So you have heat losses. So even if you capture some heat, still the efficiency is lower compared to pumped hydro.
Thank you.
Already, I'll get back to Ian then. Okay.
Yeah, thank you so much, Ramesh. It's so informative, and it's such an interesting dive into, a constantly changing environment. So thank you so much for that. And I'm sure that there may be some other questions that'll come up as well. I will go ahead and take screen sharing back from you, my friend. Let's
Yeah. So let me see
go
how
ahead and do that here. How are we looking? Katie, could you or others confirm?
Um, yeah, it looks good.
Okay,
uh,
perfect. So we will try and be expeditious here. I want to make sure that we've got enough time for, our
uh,
EPRI friends to They're full-time for the presentation. I will just note that the content here is also available in some other recordings we have online. We're also happy to provide one-on-one technical assistance to local governments who are considering enacting zoning regulations or other or would like more information so that they can consider what battery storage means for their community as the local regulatory authority. I know that there's one remaining question which has to do with local land use authorities, so I'm gonna, hopefully address that as we go here. But Katie, if there's anything I missed, please feel free to let me know. The photo you see in the background here is a community solar installation paired with a battery storage facility in central New York. In total, I believe it's 10 megawatts of solar and I think a 10 megawatts of storage as well across two installations that are co-located next to each other. So the first thing that I will say, and did that advance the slide? And I'm sorry, I cannot see my own screen. So
No, it did not. It did not advance. You're still on planning and zoning consideration for energy storage.
not
There you go.
anymore,
Now
I'm
you
not.
did.
There we go. Okay, perfect. So the good thing I'll say here first and foremost, with a bit of not joke, but the first thing I'll say is that congratulations, because every community that's on the call here, assuming that we don't have New York City folks on the line, everyone already has robust enforceable regulations in place to ensure the safety of battery storage, and that is because the fire code was updated. And circa January 1st, 2026, you have nation-leading fire safety considerations in place for battery storage within your community. And that's really important, but that's only one piece of the puzzle. That does not talk about local land use and zoning. And so there's the question of, even if you already have your bases covered from a fire code perspective, that is not the only thing that goes into land use and planning decisions. So why should local governments otherwise be proactively thinking about and planning for energy storage? There's a few reasons. The first one would be that there's a lot of different use cases. I know this one of the other questions that came through earlier also talked about proximity to residences, right? So I guess that's two questions that have come in about residential proximity. Um, we're talking about a technology that scales down to be a residential installation, right? We're talking about commercial installations like this one at a office park in White Plains, where there's no solar involved. It's just a standalone battery that's connected to a commercial customer, providing them with bill savings in a very expensive part of the state. Um, this here is another example of a community solar project on a rooftop that's paired with a battery facility in the parking lot next door, up to a larger 20 megawatt battery system out in Western New York that's standalone. And this is an example to the other question that came through earlier of proximity to residences being part of it. You can see within, I'm not sure the exact setback between this facility and the houses behind it, but I would guess it's, less than a quarter mile to the closest residences. And this is a great operating project that's, meaningfully providing value to the grid out in Western New York today. Um, so there's a lot of use cases, right? We understand that when we think about planning for energy storage, we're not talking about one thing. We're talking about a technology that can be scaled and sized for different things. Now, what do all of those use cases and installations have in common? And this is getting to one of the other questions in the chat regarding, local oversight over projects. All of those use cases and installations that you just saw on this slide, they are all subject to local permitting authority, which means they are subject to the municipal administration of the state environmental quality review process, as well as any other land use regulations you have on the books. This chart here outlines what I'm talking about. So some of you may be familiar with the process in place for large-scale renewable generators like wind and solar, whereby projects that are larger than 25 megawatts are permitted by the Office of Renewable Energy Siting within the Department of Public Service. That agency is sometimes called ORES as an acronym. So ORES, you can see the middle column here where their jurisdiction lies, right? So for a generator like solar and wind, anything above 25 megawatts of generating capacity is permitted by ORES. Whereas for a battery, the bottom two rows, whether or not something goes through the state level permitting process depends on if it is co-located with renewables. So if a large-scale solar and wind project has a battery component, then all of those would be subject to permitting by ORES. But if it is a standalone battery, or if it is a battery paired with a solar project or a wind project that's under 25 megawatts, those will be subject to local permitting. So, from my perspective, I would say I would always recommend that municipalities consider whether or not they are positioned to take action proactively to establish regulations to ensure balanced and well-considered um, development in their community. And that includes energy storage because it's within their jurisdiction. Um, and so that means everything, again, from the small residential stuff to the large grid serving stuff, those are all, if they're standalone, subject to local permitting. Photo examples of what we're talking about, and I apologize where there are duplicate photos. I tried to not, but some of them end up being duplicates. Every project you see here, whether it's the solar or the storage, those are all examples of projects and installations that would be subject to local permitting. So that is why it is very important from our perspective that municipalities take the time to consider this, hopefully proactively, hopefully before you have an application in place. But if not, in response to an application is, sort of like the proverb, right? The best time to plant a tree 20 years ago, second best time is now, right? You don't want to wait until you find yourself in an unfavorable position with regard to a pending application. So we talked about use cases, talked about local permitting authority. A couple of other reasons that we think people should consider, meaningfully planning for energy storage at the local level. The next one would be balancing constituent and shared benefits with impacts. And what I mean by that is I've seen examples of communities that have gone so far as to ban energy storage wholesale within their jurisdiction. And what you do when you take such a black and white, and I would consider, not nuanced approach to a technology, is you're not only saying that you can't build a large grid serving system, but you're also ensuring that any resident or business within your community has suddenly lost access to one of the few tools that they have to reduce their energy costs, right? To reduce their electric bills on a monthly basis. I don't think that any local governments will keep, if they were really perceived as, stepping on the toes of their constituents, they may not have a job for too long. So I think really it's behooves them to take a well-considered approach to at least understanding the differences between some of the types of technologies and installations and trying to think about regulations to, ensure a balanced approach to deployment that is responsive to their constituents, including the benefits that those smaller systems can provide. And then finally, the reason to consider a plan would be to move beyond moratoria. Land use moratoria are a really important tool in the local land use toolkit. They are not a permanent solution. And the longer that moratoria get extended without a real resolution or without a demonstration of tangible steps being taken in the meantime, the worse you can position yourself in terms of, opening yourself up to liability as a local government. And so we think it's really important to make use of the tools and resources available to you, including local, zoning templates and model laws, laws that have been adopted by other communities across the state, resources available from, organizations like the Tug Hill Commission and Cornell Cooperative Extension and others. These are all really critical things that I think can help communities take a meaningful and well-considered approach at the local level. Um, there's a few considerations that are relevant for all energy technology. Proximity to electrical infrastructure and the capacity of that infrastructure is important. Thinking about appropriate locations in terms of zoning and districts, thinking about bulk and area standards, environmental impacts, visual impacts, ag impacts, decommissioning, taxation. Those are things that are, largely relevant for any technology. When it comes to storage, there's a couple of those that I would say become a bit less important and some that become a bit more important. So, visual impacts and agricultural impacts. It's not to say that they're not important for battery energy storage, but the reality is that when you compare batteries to something like solar or wind, they're a much smaller footprint and they're much less, potentially intrusive, right? You're talking about a smaller modular containerized type of technology. It does not have multi-hundred acre footprints. So the amount of agricultural lands being displaced or the amount of visual impacts that are occurring are a lot lower than maybe for other technologies. However, fire safety and incident management training for local first responders, those become really important considerations. The good news is that those are predominantly addressed by the fire code, which again is already in place in the community without the need for local action, and we will talk more about that in the final part of the presentation tonight. But just want to note that, some of those other things that you may have been asking yourself when you were considering adopting a solar law are also relevant here, right? Mapping is a really good first part of it. And if this is something that would be valuable to you in your community, I would really encourage you to reach out to NYSERDA, whether it's through our team or our amazing regional energy advisors who are working with local and regional planning organizations to help provide technical assistance to communities like your own. We can help with this, right? So this is an example of a map that a colleague recently made that I think does a really good job for helping inform community planning around energy, right? This is a zoning map overlaid with existing grid infrastructure, and it can show you, based on the transmission, the high level, high voltage transmission, or the lower level distribution infrastructure, where you might be able to see potential applications for battery storage in the future. And you see how that grid infrastructure aligns with the underlying zoning districts, and that can help allow you to inform where these projects might make sense as an allowable use versus where, you might have more concerns. So, right, this is a really good way that you can help avoid some of the denser residential areas where possible, if you can, find opportunities to allow storage in places that can make sense from, a multi-factor, multidisciplinary perspective, not only thinking about grid infrastructure and not only thinking about zoning, but thinking about how those things interact in tandem. There's also multiple ways to go about, implementing a regulation, right? You can do a conventional zoning approach where you say something to the effect of, larger scale batteries are only an allowable use in the industrial and commercial and highway districts. They're not allowed in the denser residential districts, right? That's one way of going about it. You could consider overlay zones or floating zones, whereby you're establishing technology-specific regulations that apply on top of those other districts on your zoning map, allow you to add more relevant protections related to that technology, but maybe you're not bound by the strict boundaries of an existing zoning district. And that way you can avoid the need for, potential use variance processes in the future, things like that. So there's multiple ways that we can go about this. Obviously, we don't have the time to go into all of them here, but I'm going to just keep us moving here. Um, we recommend, as we do in the NYSERDA model law, to establish definitions to enable that appropriate zoning. Our model law has a two-tier approach, which is based on a threshold that establishes requirements that are more stringent for bigger projects in the fire code. So it's our laws, as it's currently written, is tied directly to a threshold established in the fire code. If you are a local government and you're thinking about, adopting a zoning regulation and you have some concerns about this, I'd really encourage you to reach out. We're happy to talk more about alternate tier structures that consider things like, accessory uses and primary uses, some of the more conventional land use parlance. We can help adapt this to work with you so that you can sort of better delineate between not only big and small, but also, bigger batteries that are supporting specifically an on-site use, meaning maybe a commercial operation or a business in your community that's above the 600 kilowatt hour threshold. But again, they want to install it because it's directly benefiting a member of the community, right? As opposed to a larger grid serving system. So I would say if you're any concerns about the two-tier approach, please feel free to reach out and we're happy to talk to you about other options. Here's some examples of what those tier one and tier two systems could look like. Again, residential, small to commercial, medium projects, right? This is a 250 versus a 940 kilowatt hour installation. The footprint is the exact same for these technologies. It's just that it's a different chemistry, it's a different product, and so the density is different. Um, we've seen some of these pictures before. You've got, a 1.8 megawatt hour system, a 2.5 megawatt hour system. I will note to the question of residential proximity that we got earlier, the photo on the right is a containerized battery that's located in New York City, and it is as the closest one to my house. So I live here in Brooklyn. I work out of NYSERDA's New York City office. I'm within a quarter mile of this installation, and more importantly than where I am is the residential proximity. You can see that this project is directly adjacent to. You can see one here, but it's actually two. Um, High-rise apartment buildings. It is right smack dab in the middle of them. It's right against a commercial operation, which is a sports arena, the Barclays Center. And this is a project that has FDNY approval, right? They went through a really stringent fire safety review process. They're complying with the best code in the world, the New York City Fire Code. And that's where it's installed, and it's been operating safely for years. I myself have personally had the opportunity to go tour it. Some larger projects. The one on the left is a 16.5 megawatt hour project. The one on the right is a 45 megawatt hour project. So these would be, upper or, larger projects that would be classified as a tier two installation in the NYSERDA model law. So yeah, overall recommendations, we think it's important to establish definitions to recognize the differences between different types and sizes of projects. We think it's important to learn about the fire code to want to avoid duplicating or having anything in your law that's in conflict with the fire code. Um, and then you want to consider, if you want to explore alternate structures or tier definitions, again, I'd recommend reaching out to NYSERDA and we can talk about it, but it's important to it be based on a well-considered, legitimate source. I would say don't just pick a megawatt threshold for the sake of it because it's a nice round number or because, there was one specific project that was 1 megawatt and you said that that's the number we want to go with. I think it's important to be a bit more tied into, other state programs or regulations that are in place, which can help you have a better argument for why you drafted your law the way that you did. And then again, I would just recommend that you consider the reality of system benefits. If something is on-site or remote or grid serving, those are different types of benefits that can mean different things to different people. Finally, I would just say within the NYSERDA model law, and I want to make sure that we close here so we've got time for Q&A at the end. We recommend utilizing different regulatory requirements for the bigger versus smaller projects. So smaller projects, we have a sample permit and inspection checklist that you can reference so that our code enforcement officials know exactly what they're looking for when it comes to permitting these smaller projects through a ministerial permit process like issuance of a building permit. Whereas the larger projects, we recommend you requiring, full site plan and special use permit reviews, as well as the administration of the fire code. Obviously, there's a lot more that goes into planning and zoning. I just want to make sure that we can get through to the fire code and fire safety portion here. So the final thought, I believe, on this section is just that for the larger systems, things that are really important would be including decommissioning planning into your local zoning, including consideration of availability of funds, right? So requiring decommissioning funding be made available as part of the approval process. Include incorporation of a public hearing process through the site plan and special use permit approvals. And then again, making sure that we're aligning with the New York State Fire Code. I'll say, from my perspective, the fire code is wonderful. It's nothing if you don't know how to enforce it. So we will be relaunching our fire code training for code enforcement officials and building officials, which is something we've been offering since 2019 and has now been updated for the new fire code. So we recognize the need to reach that critical audience. That brings us to the energy storage and fire safety. Katie, I am sure that there are questions there, but I think it would be great if we can keep moving to fire safety just to make sure that we don't cut the EPRI folks short. And then I'm happy to stay a couple minutes long for questions if we need to.
Sounds
Does that
good.
work for you?
Yep.
All right. So finally, before I turn it to Erin, I'll just note again, you've got a co-located community solar and energy storage facility here. It's actually two projects, so about 10 megawatts of solar, 10 megawatts of storage that are located directly adjacent to one another. And we're here to talk fire safety. So I will turn it to our colleague, Erin Minear from EPRI. And Erin, just give you the next slide. Know this when you're wanting me to move on.
Yep. Thanks, Ian. I'm glad to be here today. Erin Minear with EPRI, the Electric Power Research Institute. I'm joined by my colleague, Lakshmi Srinivasan, who leads our technology and safety area. Got a lot of slides here, but I'm going to go through them pretty quickly and just feel free to ask questions. Lakshmi can answer them in the chat. We can do them at the end as well. But want to provide an overview of energy storage safety, really focused on what we know from real world deployments, what we've learned from past incidents, and how we can take those learnings and incorporate them into design, standards, emergency response, and to protect the community. So the goal here is to provide some context and clarity around risk and impact to communities and how safety practices evolve as we continue to scale deployment. So the next slide is just an overview of who is EPRI. I think there was one question on this. We are a nonprofit independent energy research organization, and we bring together with a public benefit mission as we bring together various stakeholders to address complex challenges around the energy sector And then Lakshmi and I's area is focused on energy storage, really looking at one aspect is safety and how we can look at objective data-driven data and through this collaboration model to guide leading practices. So we can jump to the next slide. Before we talk about specific safety risks or individual incidents, it's helpful to take a step back and really look at the bigger picture of how energy storage has grown over time and how incidents have occurred over time as well as deployment increases. So this helps to ground the conversation with overall trends rather than talking about a few specific incidents. Which we can kind of highlight a few later and what we learned from them. So the key takeaway here is that deployment is rapidly increasing, but the failure rate, so the number of incidents or failures per gigawatt hour of deployed has declined over time. And that's the orange line on the chart here is the rate of incidents and how that's declined relative to how much has been deployed. So we're seeing that incidents are rare compared to total deployment, and also that we are learning as an industry. And we'll talk to how we've grown and some of the things that have contributed to the learning, including incidents and codes and standards. So we haven't fully eliminated the risk. We are still seeing incidents, but we are showing meaningful progress. And what we'll also show later is that we're minimizing the impact of these incidents as well. The next slide provides some additional background context on how to think about safety. So this is what EPRI's perspective and how you think about it. We need to understand what the different failure mechanisms are. And we think about prevention. We think about how can you think about siting or installation. So there's that prevention aspect. And then there's a mitigation. So if there is an incident that occurs, what does that look like from an emergency response perspective? What do we want to do to monitor that incidents to inform actions taken by first responders? And then how do we address the recovery of the site afterwards? And then education is a big piece. So we want to make sure people are informed about the actual hazards that are there, the risk that is there, so that you can make informed decisions about how you would approach an incident from a first responder, or how you think about permitting and siting, and how to interpret results from testing and other things. So that's our approach to safety, and we want to make sure that it represents that it's many different aspects. It's not just one thing we're focused on, but sort of layers. And I think the next slide gets to that same point about layers of controls, layers of safety. So when we heard about different types of energy storage, this chart here speaks more to battery energy storage systems, but I think you can apply it more generally. You can think about the smallest unit and how, say, battery chemistry may impact safety. So there may be some certain type of chemistries that are more inherently safe with their features, but you can't just take it with that. You need to think about how that's integrated into the larger system and protections layered along that, which can be controls, it could be ventilation, it could be fire detection, many different strategies when you build an energy storage product or system. And then when you site that system, how you think about how you might space them. So what's the distance in between two battery energy storage containers? And if there's an incident with one and one catches on fire, you limit the incident to that one unit. And so the impact of the incident decreases accordingly. So this kind of shows that we're thinking about system safety across all different aspects, from the chemistry all the way to the environment. You can go to the next slide. So we saw that learning curve. We saw that the rate of incidents is decreasing relative to the amount of storage deployed. And part of that is because we have learned from incidents. We have understood what happened, and made adjustments across the industry. So if there was, fires and explosions, what caused that? How can we think about the risks associated with, say, gas buildup that led to an explosion, and what mitigation measures can we take in place, and how can we inform first responders to adjust accordingly? And so kind of these incidents are just a select few that highlight a progression of you have fires that propagated, you had some injuries in some, and then moving on to later incidents, as we learn from them, the fire could be limited to a single unit, or we could reduce the amount of or eliminate the injuries and fatalities associated with some of those later incidents. So that's kind of the progression there. And then building on this, the next slide shows sort of layered how codes and standard evolution has aligned with some of that incidents, and how we've taken those learnings and applied them and to make increase the safety of and information informed decision making on future projects. And I know Ian has some slides on providing codes and standards within the New York context. So this is an evolving process. The latest editions of the National Fire Protection Code and the UL Large Scale Fire Testing standards were recently updated. And so to include large scale fire testing, so we're getting more information, more insights, all those learnings, and that's contributing to that reduction in the failure incident rate. We have a few other slides talking about, again, lessons learned. What have we learned from past incidents? And this one looks at injuries and fatalities. And we, so I think couple key takeaways here. This is a global look. Most incidents do not result in injuries. The ones that did, 6 of the 11 that we've identified here were related to an explosion, and most of those were first responders or on-site personnel, and not the general public. In the United States, if you look at the bottom graph, there was an incident in 2019 in Surprise, Arizona, where there were some firefighters injured. A lot of lessons learned from that incident, and we have significantly improved. And since then, there haven't been any injuries associated with energy storage incidents in the United States that have been reported. So this kind of reinforces the importance of training and situational awareness in those protocols. So this, if we want to go to the next slide, so we've talked about injuries, and while they're rare, we also want to think about civic impacts and what should be considered there. So civic impacts may include road closures, shelter in place, evacuation. A couple things to highlight here. In many cases, these decisions were made out of an abundance of caution. So in the lack of real-time data and monitoring, those decisions were made to protect the public. And so if we think about how we progress and minimize the impact, the civic impact moving forward, we really want to focus on data-driven decisions and what we can do to protect the public and public safety, but proportional to the scale of the incident. Again, thinking about minimizing that impact there. All right, I think we can move to the next slide. And so, up to now, we've talked about incidents that have happened in the real world, and so the impacts of those. But I want to just take another step back and talk about the hazards and lay out some of those hazards and which ones really we want to think about. So the next few talk through the hazards. This one is general to energy storage. The next one gets into lithium ion. And even within lithium ion, these are the ones that we've identified for lithium ion. Some of these are So not unique to lithium ion, but representative of other battery energy storage systems. I think the one to focus on here would be the fire and explosion risk. And so this is something that would happen under an abnormal condition. Typically, it would be initiated by a thermal runaway. And thermal runaway is a irreversible failure mechanism where a battery cell experiences a rapid internal temperature increase, and that can release flammable gases, and that heat can propagate to cells and to other modules and racks and potentially the system. So it can be a cascading failure, and then if it's not mitigated. So when we think about mitigation strategies and we think about again, that idea of layering of controls, minimizing propagation is one way to, again, minimize the impact of an incident. So during some of the thermal runaway, it can release a mixture of different flammable and toxic gases. And this is what we need to consider when we're thinking about first responders who may be approaching the site, and how the composition and the quantity of the gas may result in an air plume, and how that air plume disperses over a community, and that's what may result in some of those civic impacts that we talked about. So again, thinking through mitigation strategies, how do we mitigate or reduce the propagation to adjacent units to minimize that? How can we think about early detection? How can we think about ventilation? And when we think about, one of the important things to think about is there's a fire risk and there's also an explosion risk. So we really want to think about trying, from a first responder, is mitigating that explosion risk. So you may hear a term called monitor and contain, which means that they may not be actively fighting the fire because they're more focused on preventing an explosion. So that framework of, we have a good understanding of lithium ion battery energy storage systems, and that framework of how we've thought through hazards and mitigation and emergency response will help us in with these new emerging non-lithium technologies. So what are the unique hazards associated with these technologies? How can we mitigate them? How can we pass that information to first responders, permitting authorities, communities, such that we're, again, mitigating and reducing the risk and the impact if there is a failure event. And so I have a couple of slides here that talk through specific safety considerations for compressed gas, which could be, compressed air, compressed CO2. This one, if you want to think through the unique hazards here, you might think about pressure, that like this one introduces a hazard around pressure and mechanical hazards that you wouldn't necessarily see with lithium ion, and potential. So you might mitigate those through leak detection or pressure relief systems. So again, thinking through what's unique about the storage technology and how you can mitigate that. And then the next slide is on the zinc halide. And what is the safety profile of this? And so one of the selling points of this as a longer duration is that it may have a lower inherent fire risk. But then you can also think about, you have to think about the sort of potential corrosive or toxic nature if there's a chemical exposure. So again, thinking through, and you can go through all of these, and this is one of the things we do at EPRI, is thinking through all the different technologies and how they evolve and what does that mean? What are the known risks and what are the unknown risks, and how can we start to characterize those unknown risks through field deployments? So those were just a few examples, because I know that those some of those are being proposed in your region. Again, the message is not that it's about thinking about what risk looks like and how we can manage those. So yeah, I want to make sure that there's plenty of time for Q&A. Really want to thank you for your attention here, and happy to answer questions now or in the chat. But I know, Ian, you have some more slides on safety
Yeah,
as well.
maybe I'll keep us going for just a couple minutes, but I want to make sure that we've got again a couple minutes, and I'm sorry for those. We're over time a bit, but we've been answering some questions as we've been going, so I think we're ultimately doing okay on the timing. Um, I just want to ground the fire safety conversation within the New York context with a couple of minutes of slides because there's a lot of really great work that's been done that deserves recognition. I will say though, even before we go into that, that the chart that you have seen that Erin presented, where you see the failure rate as it compares to the volume of deployment, I just want to say, you know, not that we've got celebrities in our midst, but like the EPRI folks, this team who we're hearing from, and the work that they're doing to document and track failures is really industry leading stuff. And if you have followed energy storage and the fire safety conversation, you probably recognize that graph, right? I mean, this is really foundational knowledge towards our understanding of developing a safe technology and ensuring that, the electric grid is supported by technology that has a place in our future. And so I just want to say thank you again to the team for the work that you do. And it's just amazing to have you here, considering again how many times I've looked at that graphic in the last, 6 years. Um, okay, a couple minutes on the New York context. In 2023, it was a bad year for batteries in New York. There were fires at three different sites across the state of New York, in Warwick, in Chaumont, and in East Hampton. And in the wake of those incidents, we convened an interagency fire safety working group consisting of relevant state agencies as well as external partners. So you had Department of Homeland Security, you had the Office of Fire Prevention and Control, NYSERDA, DEC, the NYPA, the LIPA. DOE-funded national labs like Sandia, we heard from Ramesh earlier, as well as other subject matter experts such as fire protection engineers and the like. That working group did a few things. One of which was analysis of data collection and assessment for environmental testing data, whether it was air, soil, or water testing data, emergency response actions, as well as the root cause analyses for those incidents in 2023. Um, as a result of that, what we found is that there were no identified injuries and no harmful levels of toxins recorded in conjunction with those fire events in 2023. Um, I would say arguably the most important thing that the working group did is that they took a keen eye to the regulations, right? We wanted to implement the nation-leading fire safety code that we could. And so they reviewed the existing fire code standards and regulations and developed recommendations to revise and enhance the fire code. As a result of that, and learning from the context in New York City, where inarguably not only do you have the density of residential and commercial operations in the city, you also have the New York City Fire Department, who have, I don't know if anyone's ever tried to build something in New York City, but you know about the red tape and the permits you have to go through. And it's because, it's the most stringent level of review possible for developing something. And the New York City Fire Department said, we can do this. We can understand what it takes to make it happen. The folks that were involved in drafting New York City's fire code had a direct role in expanding it to be part of the New York State Code. And so, as a result of that, starting January 1st of this year, we have the best fire code in the country. It is the most stringent review requirements and technological requirements that you can have to ensure the safety of a battery storage installation from a planning perspective. They also did a bunch of inspections of the in-service battery storage fleet, and as a result of those inspections and what they learned, they were able to update and enhance our safety inspection protocols and checklists that are part of the approval process for batteries in the state of New York. Um, Initial fire code went into effect in 2020. I'm going to skip some of this just because if you're interested in the history of the codes and the evolution there, please reach out to me. But I want to, be expeditious with our time. The key things to know, if I can just summarize a couple of them. The first thing to know, number one, local governments are not on their own. There is a hard requirement in the fire code that the applicant funds a peer review of the application so that there is subject matter expertise available to support the local officials, which means when your planning board is reviewing an application, when your town board is reviewing an application, they are not alone. The developer has to pay for an agreeable third party to be part of that review to support the town. There's also a requirement in the updated fire code for project-specific emergency response plans, which are to be developed in conjunction with local fire departments, um, which is great, right? We want to make sure that from an early perspective, from an early, standpoint, from an early checkpoint, that these applicants are reaching out to and working closely with local first responders so that none of this is happening without their participation. Um, Speaking of participation from the local first responders, the fire code requires project owners to provide annual on-site trainings and plan reviews. What that means is that no one is coming in, building a project, and then disappearing for years at a time, right? You don't only hear from them on tax day and if something goes wrong. On an annual basis, there is a requirement that they provide access to the site to do an on-site training and a review of the emergency response plans. And then finally, a critical requirement, speaking of people not being alone, is that the fire code requires that the project owner furnishes what we call hazard support personnel, which are there to support and collaborate with the first responders. And those people have to be dispatched. If there is an event, if there's an incident at the site, they have to be dispatched within 15 minutes and on site within 4 hours. I know what you're thinking. 4 hours seems like a long time. Obviously, it is there to accommodate the fact that some people are in more rural and hard to reach parts of the state than others. But no matter what, because there is real-time monitoring requirements when there is an incident under the current fire code, emergency response or hazard support personnel rather will be dispatched by the project owner and will arrive on site to work with and potentially relieve the local first responders from active duty if everything is under control and there's no active fire or safety concern. So there's a lot more that goes into the fire code. Those are just kind of high level things that I think are really important. If you're interested in learning more about what's in the updated fire code, we're happy to send these resources around or answer more questions. With that in mind, I think we've got, about 15 minutes, a little shy of our half hour that we targeted for Q&A. I'm realizing now there's one more thing I want to, or I mentioned peer review. One more thing. We have our battery storage guidebook for local governments. It includes the model law, the model permit, and additional information about fire safety. We'll make that available, and you can have the links accompany the slides and the recording of this presentation when the commission sends them out later. Our team is also available for hands-on education and technical support for communities, so please reach out. I put the email in the chat earlier, but it's cleanenergyhelp@nyserda.ny.gov, and we'll be happy to support your local government and your community as you consider taking next steps to regulate these systems. We've got pre-recorded trainings. I mentioned our clean energy advisors in the region earlier. There's also resources from the Office of Fire Prevention and Control. They have a lithium-ion battery training course for first responders. There's deliverables from the Fire Safety Working Group. We've got public access to the code books if you're interested in those. All of this stuff and more will be yours for the low cost of $0. Just please reach out if we can be of service to you guys. And with that, I will stop talking and we will do some Q&A.
So one question we had was regarding the training for the fire personnel, and I know that that's provided, but there's a second part to that question. What about any special equipment that the fire department might need, the local fire department might need to have? Is there a way to get that funded by the project sponsor?
Yeah, absolutely. I have found in my experience that developers are extremely interested and willing to work with communities to make sure that they are supported. I will say there's not, to my knowledge, a ton of equipment that is typically necessary, depending on how well resourced the incident responders are. So recognizing that there is variability from fire department to fire department. But the short answer I would say is yes, absolutely. Talk to applicants about potential equipment needs, and if those are identified, I have found that applicants tend to be very willing participants to providing and funding equipment needs. Sometimes that's done as part of a larger host community benefit package, right? So in addition to, a pilot agreement or a tax agreement, sometimes a community will negotiate an agreement with developer to do things like funding equipment or contributing money to municipal projects, things like that. And so I would say where you have concerns about the resources of first responders, absolutely bring those up in conversation with the applicant, and I'm sure that you'll be able to find a workable solution.
Okay, thank you. We have a question about the electrical storage in the panels themselves. Is that covered in the fire code? I'm not sure exactly what that means. The electrical storage in the panels themselves. Tom, if you want to maybe clarify that question a little bit. Another question was earlier on, are all of these projects, specifically zinc halide and compressed air, going ahead? What are their capacities and expected timelines?
Yeah, so capacities and where they are in the process, I can certainly send you. There's publicly available information for all of the projects participating in the NYSERDA procurement. Some of the details I am not aware of because I'm not part of the, adjudicating committee reviewing those applications. And a lot of that information is not made public until award decisions are finalized. But I would say that to the point of whether or not they move forward, projects typically, not necessarily, but typically, seek or require incentives to be able to move forward. If a project were not to receive an award from the current NYSERDA procurement, nothing would preclude it from applying again to the next year's solicitation. So, to the extent that the projects are all moving forward, it will depend on the financials of the project and the permitting of the project. The permitting, again, is all subject to the local governments and their permitting jurisdiction. So, the question of timing and the question of whether things move forward, I will send you all the publicly available information for participating projects that we have. But for questions about like, a project moving through local permitting, if it's not answered in those resources, you may consider reaching out to the applicant or even reaching out to the town to understand where they are in the permitting process.
Okay. Another question. Electrolytic hydrogen is often hyped in the media, but wasn't discussed here. What is the feasibility of this type of energy storage?
Yeah, Ramesh, I'll tap you to chime in here because I know that you did briefly mention hydrogen, but obviously we're focused more a little bit less on some of the chemical storage technologies. I would say that one key thing here is that, like other technologies, some of these technologies, including hydrogen, are subject to changing priorities of a federal administration. One of the big things affecting hydrogen technology is the availability of tax credits, which I believe may have sunsetted or may not be as rich as they once were. So that's not the technical feasibility part. That's more of a policy consideration. But Ramesh, you might be able to speak to the technical feasibility of electrolytic hydrogen.
Right. You are correct, actually. Uh, Past administration put in a lot of funding for hydrogen. That funding gone away pretty much. Um, so electrolyzer, using electrolyzer to generate hydrogen, then you need to store hydrogen, convert that hydrogen into power. The whole round trip efficiency is low, but still people are looked at the technologies for um, because of seasonal storage. For a very long duration energy storage, you can store it. So one project that's been going on in Utah, a demonstration project with Mitsubishi Electric. They are digging big um, caverns in the ice, in the salt, in the salt mines, and then to store hydrogen there. And then they want to run it with gas turbine to generate electric power. Right now, most of the turbines, they don't run on full hydrogen. They have to mix with some natural gas. So I think they're using a 30% initially hydrogen and rest natural gas. So there are still some demonstration need to be done on that part of it. The electrolyzer part is well established. Um, and fuel cells are still expensive to really use it in large scale.
Thank you. Question back to some of the zoning items, especially particularly related to residential. If BESS is allowed in a residential zone, what additional safeguards should planning boards demand as a condition of approval? And maybe that's covered in some of your model laws, but if you could just touch on that real quick.
Yeah, I mean, so the short is that, again, municipal permitting jurisdiction applies to standalone battery storage. And the important thing there is to consider proximal uses, right? I think depending on the layout of electrical infrastructure in your town, you may or may not have residential, dense residential development or any residential development near these existing systems. Now, I know there were other questions earlier about that as well, which is to say there are installations in New York that are proximal to residences. I showed a photo earlier, one of the, again, largest battery projects in the state of New York at 20 megawatts, which is not that large relative to, what we see in other states and some of the proposed facilities in New York. One of those is, pretty close. Again, I would guess within the quarter mile, if not closer to, residential development. Again, I live in New York City where you've got operating facilities that are close to residential developments. So you can, have projects that can be, an allowable or agreeable use in a residential area. It'll just depend, and municipal governments do have the pen on zoning districts for that. So I would say, from my perspective, you certainly want to avoid, if possible, based on infrastructure, making large grid scale systems allowable within very dense, residential districts. And so what are some things that governments can do? You can establish reasonable setback requirements. You can establish, alignment with the fire code in terms of things like incident response planning and emergency management planning to ensure that you are considering proximal residential developments near the facility, right? You want to make sure that if there is an incident, that someone knows that they need to not only respond to the incident there, but also have someone in place to communicate that to local residences, or local residents rather. Yeah, so I would say that the fire code does not explicitly get into residential, proximal uses because the fire code is it's not land use planning, right? It's not a zoning document. It is a fire safety document. And so the fire code is probably not the best source for like residential proximity concerns. I would say reach out to NYSERDA, take a look at the model law, and if you've got other thoughts on, potential ways that we can consider residential uses, I'm happy to brainstorm with you or show you some examples of how other communities have approached it.
Tom clarified his question a little bit. When the panels are live during the day, how is the power they are generating? I guess I'm not, and is this in the fire code? How does the fire
I'll
code address the
I'll
panels?
take a little stab at it, but Tom, I think there's a chance that we might be misunderstanding as well. So if we don't adequately answer your question, feel free to reach out and can try and do so. Short answer. So I think that some of the things that's throwing us is the use of the language panels as opposed to energy storage, right? So solar panels generating electricity, energy storage storing and then dispatching that electricity. Um, there is a separate chapter of the fire code for solar installations. Most of the provisions within the fire code chapter have to do with like building and structure mounted solar because that's the primary consideration of the fire code. Whereas the electrical code, NEC, National Electric Code, which is, yeah, as part of the New York State Uniform Code, that has separate requirements for like the electrical engineering and wiring of the facility. The short answer is yes, fire code and the National Electric Code have jurisdiction over solar. There are code requirements in place for solar. Separately, for the standalone or paired battery storage component, there are separate sections of the fire code that are managed there. And again, if you've got specific questions that I am not addressing there because of my, maybe misunderstanding of the question, please feel free to reach out.
So we're just about 8 o'clock. I think we've answered most of the questions. There's a lot of information in the Q&A that we've answered. I may try to copy and paste that and send that out with the slide deck and the link to the video so we don't lose that information as well. Any last minute comments from any of the presenters before we wrap it up for the night?
Yeah. Thank you for the opportunity to present. Yeah, you can reach out if anybody needs any information. Thanks.
Thanks very much.
Well,
And Erin, thank you as well. I would just say again, like I personally, I'm so grateful for, Ramesh and Erin and everyone from your teams who have made yourselves available, whether through information sharing or by participating here. I just think that like, a lot of the times, the reality is that communities and local governments often don't have an opportunity to learn about this stuff unless it's from an applicant with a pending application in their town. And I think it's incredibly important to be able to get information from folks that don't have a vested interest in a specific project in the place, but are really just trying to help people understand what it means to live in a society that has and uses an electric grid. And I think we all want to continue doing so. And so I appreciate you guys and the time that you spend to try and help us all learn what that actually means, and how we can, have a balanced approach moving forward. So my thanks to you two, and Katie, thank you very much for helping create the space for this conversation.
Absolutely. There's a few more questions. We'll deal with those later. And I also was remiss. I have a couple of my staff here on this webinar as well, Maria Covey and Matt Johnson. They're planning director and planner in the office. So, feel free to call us as well, and we will either try to help you or connect you with the resource that you need. So thank you all for coming out tonight, presenters and attendees. This was very good, very dense, a lot of good information. So we appreciate the opportunity to host this webinar.
Thank you. Bye-bye.
Thanks, Katie.